The Bellwork question today. Which is heavier, a piece of wood or a piece of steel? Hey, most people want to say steel, but a redwood tree is heavier than a paperclip. A piece of wood is heavier than a piece of steel. But a car engine is heavier than a toothpick. A piece of steel is heavier than a piece of wood. Which is heavier? Depends on what size it is. Okay, but you wanted to say steel. Even the people who said it depends on the size wanted to say steel first and had to stop and think about it. Why did you want to say steel first? It's because if they were the same size, the steel would be heavier than the wood, right? You put that little qualification that I didn't put there, right? And that concept you have that the steel is that steel is heavier than wood, that's density. It's not that steel is heavier than wood, steel is more dense than wood. Okay? Steel is not always heavier, but steel is always more dense. Make sense? In layman's terms, how heavy something is for its size. Okay, you turn those into science words, and you write that. How heavy for its size, and a comparison, that would be ratio of mass to volume. Okay. And when you write math sentences like that describes a mathematical equation. Because a ratio means something over something, right? That's what a ratio is. And the something over is supposed to be mass to volume, so that sentence is this equation. Density equals mass divided by volume. Now, notice I could say that if they were the same size, the steel would always be heavier than the wood, as long as they were the same size. So what that's telling me is the density doesn't change with size. So the density is the same, independent of what size it is. If I take a brick and throw it in water, if I measure the density of a brick, and then I cut the brick in half, that half a brick weighs half as much. So its weight's gone down. But it's also only half the size, so its volume gone down. So if I take half the weight divided by half the size, I end up in the same place. It doesn't matter how much I have. Which means you can use it to identify stuff. Or you can definitely use it to rule out stuff. There may be several substances that have close to the same density, but there are lots of things that are far away in density. So you can definitely eliminate and narrow which thing you're talking about just from density. Gold has a high density. And one of the first sciencey stories told in history is about density. And it's got to do with gold. Archimedes was a famous mathematician and engineer. And the king came up to him and said, I got a problem. My problem is this. I gave some gold to a jeweler and said, make me a crown. The jeweler has given me the crown back, and the crown weighs just what the gold weighed when I gave it to him. But I think he cheated me. I think he put other metals in with the gold and kept the gold for himself. Okay? Archimedes, you got to help me prove that this guy cheated me. So, Archimedes thought long and hard, and one day he got in a bathtub and the water overflowed. And he says, that's how I'm going to solve it. He was so excited, he jumped out of his bath, ran down the street shouting, Eureka, which is Greek for, I have found it. Okay? He says, well, what's the bath? Well, he said, okay, the gold, this much gold takes up this much space. Anything that's not gold is going to have a lower density than gold. So the same weight is going to take more space. So if there's something that's not gold in this crown, it's got to be bigger than the gold it's taking the place of. So all he did was take a tank and fill it all the way to the top with water and stick a weight of gold, that the equal weight that the king gave, and put it in the water, and the water overflowed. And then he took the gold back out. And the water went down by how much space the gold took up. And then he took the crown and put it in the water. And the water overflowed. Which means it had to take up more space than the crown did. Because if it took up the same space, it would have been right to the level. But the water overflowed. That told him that that crown took up more space than pure gold. Which meant it wasn't pure gold. There was something else in it. And the guy lost his head over it. Okay? You don't cheat the king. Okay? So that's the first density story. It's the fact that anything else gold is so high, there's only a few things with higher densities, and they weren't around then. So anything he put in had to be lower density. Okay? Air's got really low density. Okay? If you need the density, if you need to know the density of something to do a problem, your book has a table on table 3.6 on page 90. So if you're assigned homework and you don't know the density of something, look it up on table 3.6, page 90. Here's what it looks like. Okay, so there we go. Okay, so notice the units are grams per centimeter cubed. Okay, so or grams per milliliter, because the centimeter cubed and a milliliter are the same size. Okay, see lead's there at 11.35. It's really dense. They did put on here gold's 19.3. So you can see if you put some lead in there, they'd notice that the lead would have to take almost twice as much space as the gold you took the place of. Okay. Liquids, they put them in milliliters instead of centimeters cubed. They got the asterisk because not all gasoline's the same. If you pull up to the pump, they got different numbers on it. That tells you it's not all the same. So that's the average. Okay. And so the numbers are in grams per milliliter. So liquids are pretty close to 1, maybe a little less. Solids can range from less than 1 to really big numbers. Okay? One of these densities on here is actually something we need you to know. That's the density of water. But we should already know the density of water. Why? Well, because of our definition of the gram. We said the gram was how much 1 milliliter of water would weigh. How much one of those little corners would weigh if it was full of water. Right? So 1 gram would take up 1 milliliter. So if you do the density equation, mass over volume, 1 gram divided by 1 milliliter, 1 gram of water divided by 1 milliliter of water gives you a density of 1 gram per milliliter. you're always going to have two units when you do density. One for the mass, one for the volume. Okay, I wrote that without any decimal points or any numbers, because at 4 degrees Celsius, that's a definition. If you're down at 4 degrees Celsius, either above or below 4 degrees Celsius, doesn't matter which, it's less than 1 gram per milliliter. So, what does this tell us? Oh no, we'll get there someplace. So we got a formula, so we can calculate density. Do what the formula tells you to do. Density will always have two units. It'll be grams per centimeter cubed, grams per milliliter, or for gases. Gases density is so low they don't bother measure a milliliter. They measure liters at a time. So gases get densities of grams per liter, and they're still tiny numbers. A liter of gas does not have very much mass, and I'm not just full of hot air. So just do what the equation tells you to do. So you got a piece of wood that has a mass of 11.2 grams and a volume of 23 milliliters. What is its density? So they gave me a mass, they gave me a volume, and they want a density. Can anybody think of an equation that has those three pieces in it? How about density is mass over volume? They're asking me for the density. It's by itself over on one side of the equation. So I'm ready to solve this. I just need to stick in some numbers. So the numbers were 11.2 grams divided by 23 milliliters equals 11.2 divided by 23. Screen fills up with numbers. How many of them can I write down? Okay, 2, because the 11.2 has 3. The 23 only has 2 sig figs. So I get 2 of my answers, so that is 0.49. And my units don't cancel out, so I leave them at grams per milliliter. Earth shattering? No, stick some numbers in the equation. Okay? Let's make it harder. There are 3 things in this equation, so as long as I tell you 2, you should be able to figure out the other one. So a piece of wood has a density of 0.93 grams per milliliter and a volume of 23 milliliters. What is its mass? Now we know this is a different kind of wood because it's got a different density than the last one. Poplar to oak. So I have a density, a volume, and I want to know a mass. And about to know an equation that has those 3 pieces in it. Density equals mass over volume. And now I'm trying to solve it for mass. So I need to get the mass by itself. That means I need to get rid of the volume. So I need to multiply both sides by volume. So I end up with mass is density times volume. So the mass is 0.93 grams per milliliter times 23 milliliters. 2 sig figs in both numbers. So I got to round it off to 2 sig figs. So that makes it 21. What about units? Well, the milliliters cancel out. One on top, one on the bottom. Leaves me with just grams, which is really good because I would measure mass in grams. It's okay? Extra super hard? Okay. They give me the equation, I just do what they say to find density. I rearrange it to find mass. Okay. The only part we haven't asked yet is how do you find volume? So, same kind of wood as the last time because it's got the same density. This time they don't tell me the volume, they tell me the mass. The mass is 23 grams. I will tell you that this version of the question here is missed a lot more than the other ones. Let me show you what people do wrong, and then you should see what's wrong with it. If you don't, I'll point it out to you. Okay, so on this one, they want you to find volume. So this is what students do. I've watched them do it for a year. They say, oh, I want volume. That means I need to get rid of mass. So I'm going to divide both sides by mass, cancel that out, and I get that V equals D over M. That is not true. V does not equal D over M. Because when I canceled out these masses, did I cancel out that line? Oh, mass was on the bottom when I started. Their volume's on the bottom when I started. It's still on the bottom. I don't have V, I have 1 over V. Okay. So, two rules of algebra? Get the thing you want up top by itself. In that order. Get it up top, then get it by itself. And whatever you do to one side, you got to do to the other. That's algebra in 2 sentences. Okay? So if I got D equals M over V, the first thing I need to do is get V off the bottom. So I'm going to multiply both sides by V. That gets it off the bottom. And it cancels out over here. So now I have V times D equals M. Hey, that's the last equation I had. Right? But now I'm trying to solve it for V, so I divide both sides by the density, and I can find the volume. Volume is mass over density. So now that I have that, the volume is mass over density. That is 23 grams divided by 0.93 grams per milliliter equals, with 2 sig figs, my calculator gives me 25. What units? Well, I got this going on right here. And what do you do with a fraction in the denominator? Remember what to do with the fraction in the denominator? Invert and multiply. So I really have grams times milliliters over grams. The grams cancel out and I'm left with just milliliters. Or you could cancel out the grams, but that doesn't get rid of the line on the bottom, so now I have 1 over milliliters. And my math teacher taught me that the denominator of your denominator is your numerator. The milliliters is the denominator of my denominator. When I invert and multiply, it's going up top. It's going to be my numerator. So the denominator of your denominator is your numerator. You never thought you'd hear the word denominator outside of a math class. Okay. So, why do we worry about density? It tells us several things. One of the things it tells us about is floating. Okay. Lower density floats on higher density. What makes it float is it takes the place of so if you put something in water and it floats, the amount of water it pushes out of the way weighs exactly what it does. If it's floating, if it sinks to the bottom, it's so dense that even if you push all the water out of the way, it's still got stuff left. It's still going to be pushed down. It's going to end up on the bottom. Lower density floats on higher density. So ice is less dense than water. Everybody agree with that? So what does that tell us happens to ice when you freeze it? Okay, just look at the formula for density. What's got to change when you freeze water? Can you get heavier by freezing something? If you weighed the water and then froze it and weighed it again, would it weigh different? Because what makes it weigh is all the atoms and molecules, and all the atoms and molecules are still there. So when you weigh it afterwards, it's going to weigh the same. But it's not going to be the same size. For it to float, the density has to go down, so the volume has to get bigger. Makes sense? It's got to get bigger. If you've ever put a soda in the freezer and forgot about it, you have learned this lesson. Because you put a soda in the freezer and you forget about it, it gets bigger, but the can doesn't. And suddenly you are cleaning a freezer because it has sprayed soda all over the inside of your freezer. I'm not wrong, because I've done it. It doesn't have to be a soda, anything with water in it. Okay? But what does that tell you about the particles? What has to happen to the particles in water? Yeah, if the volume goes up, those particles have to get further away from each other. That's the only way. The water molecules have to get further away from each other. That's the only way you can make it bigger. Right? There's no other way for it to get bigger than the molecules get away from each other. And that leads to a common mistake when we talk about states of matter. This is what, and I'm sure you may have heard it from your 8th grade teacher who said it wrong. This is not correct, but this is what a lot of students think. Molecules have lots of space to move. Liquids have less space. Solids even less space. That they say the difference between solid, liquid, and gas is the amount of space, and it's not. The fact that water expands disproves that. Because in water, the molecules are farther apart. That's not less space to move around. That's more space to move around. So it's not about space. It's not about how much room they have. It's about how stuck they are to each other. Okay? And apparently in order to stick into a solid, we said a solid had a pattern. Well, the pattern in solid water has got to be further apart than the lack of pattern in liquid water. That in making that pattern, you got to make some empty space. Those molecules have to move away from each other. Now, we think that everything does that. No, actually, 97% of things sink in their own liquids. Anybody ever melted? If you do, the melted wax, solid wax is at the bottom of the dish. If you're melting chocolate to make candy, you can't see whether the chocolate's melted because all the solids are still at the bottom. Because most solids are denser than their liquid. Ice is bizarre in that it's not. Most wood is less dense than water. There are a few of the hardwoods that are actually a little bit more dense than water. Not very much more, but a little bit more dense than water. Some tropical hardwoods are that way. That's why I said most. Helium's less dense than air. How do we know that helium's less dense than air? put it in the balloon, it goes up. What happens if the balloon pops? Helium keeps going up. And it keeps going up until it leaves the Earth. So every time you pop a balloon, you are ridding the Earth of helium. Okay? And there's a helium shortage. In your lifetime, helium is going to get really expensive. You're not going to get helium balloons because helium is going to get really expensive. It's hard to get. We'll talk about where it comes from later this year. Okay. A ship is less dense than water. Well, we all know a ship is less dense than water. But ships are made of steel. Ships are made of steel. Steel's not less dense than water. When I went to the University of Michigan, they had a naval engineering. One of the things you do was naval engineering, and every spring they had concrete boat races that the seniors had to build a boat out of concrete and race it down the river. How do you get a boat made of concrete? How do they float? Because steel doesn't float, concrete doesn't float. How come boats and ships made out of those can float? It's not the steel and concrete that's floating. Okay? Because that's not all that's there. There's a bunch of empty space in a boat. A bunch of air. And if you replace that air with water, that boat no longer floats. It's got a whole bunch of air, you drill a hole in it and let the water take the place of the air. The boat sinks. It's the air that makes it float. It's the trapped air. Okay. So to show you that it works on all scales, that it's not just that boats float on water, I found a little video I want to show you. Okay, so what they've got here is they've got an aquarium, and that aquarium is full of a gas called sulfur hexafluoride. Sulfur hexafluoride is more dense than air. So they're going to be able to take the top of this, and the sulfur hexafluoride is going to stay in there because it's more dense than air, so it won't float. It's going to stay in there. So the sulfur hexafluoride, it's colorless, odorless, so you don't even know it's there. Okay, and what that is a piece of aluminum foil turned into a little bowl. A U-shape, they made a U-shape and then sealed the ends. Okay, so the aluminum foil is floating. Why? Because it's less dense because that aluminum foil is full of air. Right? Just like a boat floats on water because it's full of air. Now, you can sink the boat. Why can you sink the boat? Well, it's the invisible water. Okay? If you did it with water, you guys wouldn't have any problem explaining it, would you? If that was an aquarium full of water and a boat and somebody did that, you would have no difficulty explaining it. Well, the exact same thing's happening, just with a gas you can't see. Okay? Now, so with that in mind, get your homework here. And so we're talking about helium. Helium floats because it's less dense. Sulfur hexafluoride sinks because it's more dense. Okay, the other thing about people do with helium is helium, they inhale it and their voice goes high. Okay? Hey, here's why it goes high. It's about density. Sounds travel faster in more dense mediums. Notice how things sound different underwater? And they always sound high-pitched underwater. That's because the sounds made outside the water hit the water, and sound travels faster in water. So when they hit the water, they get sped up and the waves get pushed together.